So if you're the kind of person who sees a really tough problem, I mean, it could be debugging code or an engineering puzzle or even just a riddle that won't let you go, and you feel that little spark, that drive to find the solution, then this deep dive is for you.
Hmm.
We're not talking about just doing math. We are uh, tearing apart the source material that gets right into the toolkit of professional mathematicians.
That's exactly right. And this whole thing is really a shortcut to understanding their strategic thought process.
A shortcut, I like that.
Yeah, because the sources, they all confirm that solving hard problems is almost never about, memorizing formulas or being the fastest. It's about thinking clearly.
Strategically.
So that complexity just kind of collapses into simplicity.
Exactly. So our mission today is pretty simple on the surface. We want to give you the strategies that, well, that scientists, programmers, designers, that they all turn to when the easy path doesn't work.
It's a framework for getting, as one source put it, dangerously good at thinking.
I love that phrase.
Me too. And if we look at the source context, one thing just jumps out right away.
What's that?
The strategies, all these tools, they only work if the mindset is right. The core attitude is this absolute refusal to stay stuck.
Okay, so let's unpack that mindset first,
Mm.
because you're right. The sources are so adamant about it. Mindset is primary.
Mm-hmm.
If you approach a problem wrong, the strategies just feel like homework. But if you approach it correctly, it's an adventure.
And the first big psychological reframe you have to make is how you deal with confusion.
Right. Most people feel confused and think, I'm not smart enough for this.
Exactly. It's a signal of failure to most of us.
Yeah.
But what's so fascinating is that a professional mathematician treats confusion as information.
Okay, that's a huge distinction.
Yeah.
So how do you make that flip? How do you go from frustration to information gathering?
You have to see confusion as a spotlight. When you're confused, it just means you've hit the very edge of what you currently understand.
So it's not a wall, it's a signpost.
Precisely. It's highlighting the most interesting, tangled part of the problem. That's where the solution is probably hiding.
So you're actually getting closer, not farther away.
You are. And this connects right into the second big mindset piece, which is that persistence.
Yeah.
It just absolutely beats perceived talent.
This isn't for some, special genius club.
Not at all. It's a discipline. It's built on focus. And the classic example, the one that defines this, is Andrew Wiles.
Oh, Fermat's last theorem, right?
Yeah. I mean, he didn't just casually solve it. He dedicated 7 years of his life to proving it.
7 years.
Working mostly alone in an attic.
And what's wild is that he first saw that problem when he was 10.
The 10-year-old kid.
And decided then, I'm going to be the one to solve this. That kind of long-term grit.
Mm-hmm.
It shows you that endurance is just part of the deal.
Absolutely. The sources really drive this home. They say you should basically tape a motto above your desk that says, I haven't solved it yet.
Yeah.
Yet. That's the whole growth mindset in one word.
And Wiles is the extreme end of persistence.
Yeah.
But then you have the story of Carl Friedrich Gauss, which shows the power of curiosity, of simplicity.
Right. Back in 1777, Gauss is a 10-year-old kid in this really dull arithmetic class.
I can picture it.
And the teacher, probably just to get some peace and quiet, tells the kids to add up every single number from 1 to 100.
What a horrible assignment.
A terrible, tedious chore, right? Meant to keep them busy for an hour. But Gauss, he looked at it and refused to believe that just, grinding it out was the answer.
He looked for a smarter way, an elegant way.
And he had the right answer, 50-50, in less than a minute.
He didn't calculate. He thought, we'll get to his trick later, but that's the mindset, is it? Don't just do the work, question the work itself.
That's it. So once that mindset is in place, we can move to the first real tool.
Which is understanding before you calculate.
Yes.
This is where I think most of us go wrong. We just start punching numbers or writing code before we really know what we're doing.
It's the number one mistake. The pros, they spend most of their time just understanding. Only a tiny fraction is spent on the actual calculation.
So what's the first step to doing that?
Rewrite the problem. In your own words, just strip away all the story, the frogs, trains, whatever. Get to the logical core.
And once you've done that, the sources have this brilliant framework. The 5 magic questions.
Yeah, they're like a critical checkpoint first.
Yeah.
What exactly is being asked? You have to define the goal precisely.
Okay, number 2.
What do I know? What information is given? What's fixed?
3rd is about labeling, right? What can I name or define?
Exactly. Give things variables. And 4th, and this one is subtle but powerful, what would an answer even look like? Is it a number, a set of steps?
Knowing the shape of the solution helps you find it.
It really does. And the fifth, this is often the one that cracks the whole thing open.
Go on.
Have I seen something like this before, even if this problem is wearing a disguise?
Ah, pattern recognition. Let's test that with a classic. The handshake problem.
Perfect.
20 guests at a party. Every single pair shakes hands exactly once. How many handshakes?
Okay, so the beginner's mistake, the calculate first mistake, is to say, well, person 1 shakes 19 hands, person 2 shakes 19 hands.
So you just do 20 times 19, which is 388.
Right, but if you stop and check your work, you realize, wait a second.
You've double counted.
You've double counted. Alice shaking Bob's hand is the same handshake as Bob shaking Alice's.
So you have to divide by 2, 190.
And that gets you the right answer, but the real aha moment comes from reframing the problem entirely.
What's the reframe?
You stop thinking about counting handshakes and you start thinking about choosing pairs.
Oh.
For any handshake to happen, you just need to choose a unique pair of people. The problem isn't about counting actions, it's about counting combinations.
So that fifth question, have I seen this before? It points you straight to combinatorics.
Exactly. It's C22. Choosing 2 people from a group of 20, the problem transforms. That rephrasing, that's the real power.
Okay, so from rephrasing, the next big tool is visualization. And the sources are so insistent on this, even if you think you're, terrible at art.
Draw something, make a table, anything to get it out of your head.
Why is that so critical?
Because it offloads the cognitive strain. Your brain is actually terrible at juggling lots of variables at once. A little sketch, a simple table, it turns this abstract mental puzzle into a concrete thing you can look at and manipulate.
The frog jumping puzzle is the perfect example of this trap.
Oh, it's a great one.
A frog is at the bottom of a 30-foot well. Every day it climbs up 3 feet. But at night it slips back 2 feet. So a net gain of 1 foot per day.
And the immediate mental shortcut is, 30 feet, 1 foot per day. 30 days.
30 days. It seems so obvious.
And it's completely wrong. It's a mistake that comes from failing to visualize the end of the journey.
So if you actually draw a little table, day 1, he's at 1 foot. Day 2 at 2 feet. Day 10 at 10 feet. What happens as we get close to the top?
That's where the visualization pays off. At the end of day 27, the frog is resting at 27 feet.
Okay.
On the morning of day 28, he makes his 3-foot climb.
And 27 plus 3 is 30.
He's out. He escapes before the nighttime slip can even happen.
The answer is 28 days. The table just saved us from that faulty logic.
It did. And that brings us back perfectly to the power of patterns, which is what the frog table helps you see. And it's what young Gauss was a master of.
Right. At their core, mathematicians are professional pattern hunters.
That's the job description.
So let's finally reveal Gauss's trick, adding 1 to 100. How did he get 50-50 so fast?
He was looking for symmetry. Instead of adding 1 plus 2 plus 3, he paired the numbers from the outside in.
So 1 plus 100.
Which is 101, then 2 plus 99.
Also 101. And 3 plus 98, 101 again.
He realized he would have 50 perfect pairs, and every single pair added up to 101.
So 50 times 101, 50-50. It feels like magic.
It feels like cheating. But that hunt for a repeatable structure is what allows you to generalize. This didn't just work for 100, it led to the universal formula for summing numbers from 1 to n.
Which is n times n plus 1 divided by 2.
That's it. You go from one clever answer to a tool you can use forever.
Okay, so what's the best habit for hunting these patterns? The sources say it's to try small cases.
This is maybe the most powerful single strategy. If a problem is huge and complex, just shrink it down until you can get your head around it.
The locker problem is a great example. You have 100 lockers, all closed. 100 students. Student 1 opens every locker. Student 2 goes to every second locker and toggles it. So closes number 2, number 4, and so on. Student 3 toggles every third locker. Which lockers are left open at the end?
Trying to track all 100 is just, it's impossible in your head, so you shrink it.
Let's do it with just 10 lockers and 10 students.
Okay.
If you work it out on paper, you find that at the end, the only lockers left open are number 1, number 4, and number 9.
And the second you see 1, 4, and 9, the pattern just screams at you.
They're perfect squares.
They're perfect squares. The lockers that get toggled an odd number of times stay open, and only perfect squares have an odd number of divisors.
That's amazing.
Yeah.
So by solving for 10 lockers, you've actually solved for 100 or 1,000 or any number.
You change the scope to find the insight.
Let's shift gears to another tool, working backwards.
Yeah, when the path forward is a total mess, sometimes you just need to start at the finish line.
The water jug puddle. This was in Die Hard 3, right?
It is famous, yeah.
You have to measure exactly 4 gallons of water. You only have a 5-gallon jug and a 3-gallon jug. No other markings.
If you just start pouring randomly, you'll go in circles. But if you work backward, you start with the goal. I need 4 gallons.
Okay.
How can I get 4 gallons? Well, I could have a full 5-gallon jug and take out 1 gallon. Or I could have 1 gallon and add 3 to it.
And adding 3 is easy because we have a 3-gallon jug.
Exactly. So
Right.
the real problem, the new goal, becomes how do I isolate exactly 1 gallon?
So what does that look like in forward steps?
You fill the 3-gallon jug, pour it into the 5. So now you have 3 gallons in the big jug.
Yeah.
Fill the 3-gallon jug again. Now use that to top off the 5-gallon jug. The big jug only needs 2 more gallons.
Which leaves exactly 1 gallon behind in the small jug.
You've isolated your 1 gallon. Now you just dump out the 5-gallon jug, pour that 1 gallon in, and add a full 3 gallons on top.
1 plus 3 is 4. Done. Working backward, just cut through all the noise.
It reveals the one critical intermediate step you had to achieve.
That leads perfectly into our final strategic tool, choosing the right representation.
This is so important. It's not just rewriting the problem, it's about how you organize the information.
Give us an example.
The classic age puzzle. Alice is twice Bob's age 5 years ago. In 5 years, she'll be 1.5 times his age.
My brain already hurts.
Yeah.
The algebra approach immediately gives you these complex equations.
Right. You get A, or flute, B5, and A plus 5, 32, B plus 5. You're dealing with fractions, simultaneous equations. It's a mess.
And it's confusing because you're tracking 3 different points in time.
The better representation, a simple time chart. Just make 3 columns. 5 years ago, now, and 5 years from now. 2 rows, Alice and Bob.
So you can see it all laid out.
It instantly makes the relationships clear and sequential. It organizes the information so that when you do have to write the equation, it makes perfect sense.
You're using a visual framework to simplify the algebra. That's so smart.
It saves minutes of confusion and dramatically increases your accuracy.
Okay, so we found the solution. We've used all the tools, but the professional's work isn't done, is it?
Not even close. The final mandatory step is check obsessively. This is the heart of critical thinking. Does my answer even make sense?
The missing dollar riddle is the perfect test for this.
It's a classic. 3 friends pay $30 for a room. The manager says it should have been $25. Gives the bellboy $5 to return.
But the bellboy is sneaky. He keeps $2 and gives each friend back $1.
Right, so each friend paid $9. 3 times 9 is $27. The bellboy has $2.
And 27 plus 2 is 29. Where'd the other dollar go?
It sounds like a genuine paradox.
It does.
But it's not. The error is in the logic of the addition. The sanity check is to track where the money actually went.
Okay, break it down.
The hotel has $25. The bellboy has $2. The friends have $3 back in their pockets.
25 plus 2 plus 3 is $30.
All the money is accounted for. The trick was adding the bellboy's tip to the amount the friends paid. You can't do that. The $27 they paid already includes the bellboy's $2 tip.
You're mixing categories. The check saves you from the trick question.
Always.
Okay, let's recap this amazing toolkit. It starts with the right mindset, then deep understanding. After that, visualizing the problem.
Then hunting for patterns by trying small cases.
And working backwards when you're stuck, and always, always checking your work.
And to really make these habits stick, the sources strongly recommend you keep an error journal. Even someone like Terence Tao, one of the greatest living mathematicians, keeps notes on his mistakes.
And it's not just a list of wrong answers, is it?
No. You track 3 things. 1, what I did wrong. 2, why that wrong step felt so tempting at the time.
And 3,
The better habit to practice next time.
that turns mistakes into your own personalized data.
It's your custom PhD in problem solving.
For anyone who wants to go deeper, the sources point to a few key resources. The Bible is George Polya's book, How to Solve It.
A must-read. And for hands-on practice, check out websites like The Art of Problem Solving or Brilliant.org. For visual learners, you have to watch YouTube channels like 3 Blue 1 Brown and Numberphile.
So you've just been handed the same strategic framework that helped Gauss see simplicity and complexity and helped Wiles persevere for 7 years. The problems you face are going to get harder.
But you now have the tools to get sharper faster than the problems can grow.
The universe is waiting to see what elegant solution you discover next. Go find something that looks impossible and refuse to stay stuck.